Hey everybody, welcome back. So we're going to talk a little bit about some of the choices we're going to make when we do these sorts of spatial analyses and visualizations. So let's get into it. So we've already talked about choropleth maps, and in particular, we can see that they're good for demonstrating things about area, about how much of an area is affected by whatever we're trying to analyze. Okay? So if we want to understand how the states vote, we use a choropleth map, right? In terms of, looking at how the whole area works. But if we were after something more like how many people are affected, then we want to use a different method, right? Because states that are large, like Montana, have huge amounts of area, but they have tiny, tiny amounts of people. So if I've counted right, then this right there should be Montana. And, oh wait, no, sorry, this one right here. That one's Montana, right? Giant, giant area, tiny, tiny number of people. Okay, so something like this cartogram on the right is a better method to answer questions about how many people are affected. So what is a cartogram? What are we looking at here? Well, a cartogram is a visualization where we try to maintain some of the topology of the real map, of a choropleth kind of setup. But we replace the details of the topology with some transformation, some sort of rubber sheet being stretched version of the original map. Okay? So in this case, the area is indicative of the number of people in a state. So let's show you an example here, right? So this little funny map is a map of which countries are too big to accurately represent their number of people. So if 1 pixel represents a particular number of people, then which of these countries has way more area than it has pixel people ratio? So the answer is most of them. Only countries like Iran and I think that's Tanzania have roughly the right amount of pixels to people. Countries like Canada are much, much too big for the number of people they have. Okay, so land area does not equate to people area. So if we did have a map which is stretched like a rubber sheet to accurately represent the number of people, then we would have a map that might look like this wonderful 8-bit rendition of a cartogram. So total world population at the time this map was made was 7.26 billion, right? And you see that certain countries like India and China are immense area-wise compared to what they look like on our real globe. And certain other countries that are, Canada looks rather tiny compared to what we expect. Okay, another kind of cartogram. So cartograms just are these they're transformed maps. Another kind that you might be more used to is like a subway map, or in this case, the London Tube, right? It just shows you how to get from A to B. It doesn't accurately represent the distance in between A and B. In fact, rather notoriously, there are stations on the London Tube map which look like they're quite far apart, and you have to make a couple of changes to get between this station and another station, and maybe it takes you 12, 15 minutes to do it. But you could have walked it in 3 minutes. Okay? So, this kind of a cartogram just is concerned with how to navigate the topological network of the tube. So here's, I think, kind of an example of where things can go a little bit wrong. This is a cartogram, rather like the one we've seen just a minute ago, of the whole world. But the problem is that the nature of the data it's trying to show, which is the share of people using the internet, so distorts the map that it's almost impossible to figure out what some countries are. Okay? So this kind of shows you the limits of this kind of approach. At a certain point, it becomes difficult, if you don't do it well, to put it congruent with the map underneath so that we can understand it in an intuitive fashion. All right, so there's a lot of different kinds of cartograms. Again, all a cartogram is just some sort of transformation of a map shape to better display data. So some of them are meant, for instance, like these Dorling cartograms, to represent very clearly the different sizes of the aerial units there, right? But it can highly distort the shape of everything. Okay, so it's accurate to the data, less accurate to the map. Okay, whereas things like these kinds of contiguous rubber sheet stretches, they're oftentimes a little bit more high fidelity to the map and can make it hard to compare the unit of data, the different size of the data. Okay, so lots of different choices. My point here is not to give you a detailed run through of all of these possibilities, because there's many of them, like we scrolled through a little bit ago. Okay, but it's important that you realize that there are different choices, and you can go out and do some research when you have to come up with a visualization like this. All right, new topic. So what about if we want to display some sort of data which has a continuous variability across a geographic area, right? Summer temperature here on the top, right? Just showing the temperature map like you're used to from TV weather. Oh, wait, you're probably not used to TV weather. You guys are all too young to have had that be part of your standard life. Right, okay, so these kinds of weather maps, hopefully you've seen. Another variation of this kind of thing that you might have seen is a topographic map. Like when you go hiking and you have all those contours on your map that show you the peak of the mountain, right? That kind of thing is another isorhythmic map, just one for elevation. Okay, so let's give you guys a little bit of practice here. So I will let you read the questions on your own. Each one of them has the same sets of answers, and your job is to figure out which kind of data goes with which kind of visualization. Okay? Good luck. And the explanations at the end of the questions will help you understand what the right and wrongs were. Okay, great. So that kind of concludes our mapping portion of this. I want to give you a sense, though, that oftentimes we want to do inference, statistical inference, on data sets that are inherently geographic in nature. And when we talk about the statistics of things distributed in space, we have a few concerns that we don't really get in our normal inferential statistics world. Okay? So, many of the techniques that we use make assumptions, right? And a fairly common assumption of many statistical techniques is that you're looking at things that might have, for instance, two variables that are independent. So they are not statistically dependent on each other. And the problem is that spatial statistics often are not independent of each other. And there's various other things like that. And so besides the problems we have, we also get an opportunity to look at the data in different ways. Okay, so because things are distributed in space, we get to look at measurements of distance or adjacency, flow between neighbors, interaction, okay? Things like that. So these are measurements which we don't commonly get in a non-spatial world. So just to be clear, right, distance is just literally in a spatial world, it's literally the distance between point A and point B, right? But adjacency is like the tube map, right? It's that two stations are next to each other on the tube map, but not how far apart those tube stations are. Just that when you leave station A, the next stop will be station B. Okay? So, right, this is what I was kind of saying a minute ago. Sorry, got ahead of myself. So spatial data has some interesting problems that don't come up in other places. There are problems of correlation, problems of picking the right, area to be defined as a region, the modifiable areal unit problem. Okay. When you're operating at the edges of maps, there's unique concerns, and there are various fallacies that mess up our ability to reason about statistics here. Okay. So let's get into it. All right. Many times, two regions that are next to each other are going to have a very similar, you pick whatever you're measuring, right? Whatever it is you're measuring. Like, for instance, house prices on adjacent blocks or adjacent neighborhoods are rarely very different. Usually nearby locations have the same housing prices, or temperature, or, traffic, okay? Anything we might be interested in measuring. And you can see that clearly from the graph here of how New York City, how Manhattan and the lower part of the island is very much hugely populated during the day and quite a lot emptier at night. Okay, people work there, fewer people live there. And so many neighborhoods are acting alike. That means that whatever this measure is correlated, right? So the measures of population are correlated between these several nearby bars. And that means if they're correlated, that might change how we do some sort of inference on them, because many inference techniques are assuming that if we have multiple variables we're measuring, that they are independent. Correlated variables are not independent. Okay, another problem we get is how we draw those bars that we were just looking at, right? Like, how did we decide on bars that were that big? What if we had lumped together like 9 bars that are near each other in a 3x3 grid and made that just one bar? Okay? So when we can choose different units to analyze, we can change the answers we get. Okay? If the spatial units of a study are specified differently, we could get a different answer. Okay, that leads us into a bunch of problems. One is that whatever analysis we do, if it's very highly dependent on how we pick our regioning, I don't have a lot of confidence in its truth value, whatever our result is. Another thing is that what if somebody's going looking for a result? Like, right, they have an idea in mind and they want to get to it. And so if you give them a researcher degree of freedom, it lets them p-hack the situation. It lets them find the thing that they want to find. So doing assignment on p-hacking hopefully will have given you a little bit of understanding of what I'm talking about there. Okay, so units are arbitrarily defined, and different organization of the units can create very different analytical results. So actually, let me show you an example of that I like. So gerrymandering. Gerrymandering is the process by which politicians can carve up the districts they represent in ways to ensure that their seat, their election, is a safe election. So in many places in the United States, politicians control how the districts are made. So let me show you how that could potentially be quite unfair. So if we have 50 people in a given area, or 50 units of people, and we have, 60% blue, 40% red in their political allegiance, well, we could do things to divide up this region into individual districts that are either very fair or not fair. Okay? If we divide up the districts like this, we get the same kind of 3 blue to 2 red ratio that we get from 60% people blue, 40% of people red. Okay? That's an even match. However, we could draw them differently. We could draw the same 5 districts with lines across like that to ensure that blue always wins in every single district. So this is a compact representation in the sense that people that are near each other are grouped together. But it's not fair because the 40% of red people are not represented in their politicians and leadership. So we can do another unfair thing where we let the district no longer be compact spatially, but kind of reach out little octopus arms into different regions in an attempt to make the district tilt one way or the other. So if we draw a bunch of districts that are meant to favor reds, but they also include just enough blues to get rid of them from other districts, but not enough blues to stop red from winning there. Then by doing that a couple of times, right, doing that 3 times, we get 3 red districts that are always going to be red, right? They're never going to switch over to blue because there's always 2 fewer blues than reds in there. Okay, but that leaves us with these kind of crazy, weird tendril looking blue districts that are majority blue, highly majority blue. Okay, so blue gets its 2 districts, but red always gets the majority. So this kind of weird shape that you see here is something that's very common in gerrymandered districts. So here's some examples of real congressional districts. So check this one out. Kind of just along a major freeway route, basically. Even ones like this that reach around back and down. It is this kind of thing that earned the term gerrymander as a name. So I don't recall the details right now, but this was originally accusing a redistricting by a politician whose name was clearly Jerry of making a salamander-shaped district, something that looked like a weird lizard, and therefore the gerrymander, the term that we continue to use here, I think like 100 and some years later. Okay, so we could redraw these districts to be compact, right? To get the right number of people that have to be in a district, because that's the way we define districts, is by representation. But yet, keep everything compact. Okay. So in going back to the problem, the modifiable areal unit problem, by redrawing districts in different ways, we can get different results. So in this, for instance, the 2000 US election was Al Gore won the popular vote by a narrowish margin. I don't remember right now, but call it like 2% or something like that. Okay. And the thing is that he lost the election because Florida went for Bush, and Florida was balanced on like less than 10,000 votes. Okay? So if we had done a different aggregation of US counties into states, it would have produced a different outcome. If one of the northern Florida counties that's on the border with Alabama was an Alabama county, not a Florida county, so we redraw the borders, right? By one county right there at the border gets included in Alabama, then those several tens of thousands of voters would have been in Alabama, which was hardcore Republican, and that would have flipped the vote in Florida, which would have given Al Gore the presidency in 2000. Now, who knows what that timeline would have looked like. But the point is not that I'm showing you how to cheat elections. The point is that I'm showing you how to think about the fact that doing an analysis and drawing the borders just ever so slightly differently between two possibilities, right, is going to potentially affect your analysis and the outcome. Another thing that you have to deal with are boundary problems, edge effects, okay? Imagine that you're doing some sort of smoothing, okay, over data. So you have raw data that's in a spatial arrangement, okay? So each one of these grids has raw numbers in it. And the problem is that, you know that raw data is too jaggedy. What you want to see is some sort of smoothed spatial function. This kind of thing happens all the time. So you just kind of do something that's like an averaging, where you take, instead of the raw number here, you take the raw number and you average it with all its neighbors. So this is a super common thing. You will see this all the time in analysis. But what happens when you're doing the averaging for something that has a border? Well, you're only getting three neighbors instead of 4 neighbors like you are at point A. And in point C, it's worse. You only have 2 neighbors. So your averaging starts to break down. This is an edge effect. And spatial data sets, you have to deal with this. Okay, you get the same problem if you're dealing with, say, flow. Maybe you're counting traffic flow in and out of an area. Okay, but you're gathering data in the United States of America from American or California Department of Transportation data sets. Okay, I can show you the California dot data. You can download it. All right, so we can get traffic flow on the freeways. But right along the border with Tijuana, there's traffic flow, right? We're getting traffic flow coming across the border, but it's not measured by American data. Okay, so we're missing a whole bunch of the traffic flow information about cross-border. Oops, right? So that can potentially affect our analysis. And of course, when two regions A and B share borders either internally or externally, there may be more similarities between them than you would want to account for in your model. So these are all different forms of edge effects. Now, another problem we get in spatial analysis is the ecological fallacy. So this fallacy is a situation where we make an analysis that's about groups. Okay, we make an analysis that's about, a region. Okay, but this fallacy also can carry over into non-spatial world. I should be clear about that. So if we make an analysis about freshmen, okay, or men and women, then it's a fallacy to use the analysis and what it says at the level of a group to talk about individuals. Okay, let's make that clear. So the logical form of this fallacy is that group X has a characteristic Y. Person 1 is in group X, and therefore person 1 has the characteristic. Okay, so the examples like men score better on math than women do. Jerry is a man, therefore Jerry is better at math than Sylvia. Okay, clearly a fallacy. Also, see height, right? The classic, like, one of the strong things is that men are on average taller than women, but that does not mean at all that any given man is taller than any given woman. So another one is, like, on average, Democrats win higher income states, and Republicans tend to win the lower income states. Okay, this is something that's on average true. Okay, but the problem is this. George W. Bush won the 15 poorest states, and the Democratic candidate that year, John Kerry, won 9 of the 11 wealthiest states. So that goes with what I just said on average, right? Yet 62% of voters with annual incomes over $200,000 voted for Bush, but only 36% of voters with annual incomes of $15,000 or less voted for Bush. So individuals who are poor mostly did not vote Republican, even though Republicans were winning the lower income states. All right. So this is a little different than the earlier example. The earlier example was a matter of essentially standard deviation, right? That even though maybe men are different than women, there's a lot of overlap, and individuals can be different than the group change. But this is a different thing. This is something that's a little bit more akin to lumping things the wrong way. Okay? So just because a lower income state went Republican doesn't mean that most voters were lower income. In fact, it's strongly the opposite, that in many cases, the higher your income, the more likely you are to vote, and the lower your income, the less likely you are to vote. So sometimes in these Republican states, it's just largely the well-off who are voting. So states can also be the other way, right? A state could be super, super rich on average because it has a few ridiculously rich people in it, like Bill Gates, right? When Bill Gates walks into a bar, the average person in that bar becomes a multimillionaire, right? So outliers distort averages quite strongly. So that's why things like this is a fallacy. Just because a group analysis might be true doesn't mean it holds true for individuals. Okay? So I think that's about enough time spent on that. So what does this slide say? It says that so we don't want to take associations about the characteristics of a population and draw them out as, as applying to individual people. There's a number of reasons why that could be false. Right. So let's crack on because we're getting past our time limits here. So what about when things are not distributed uniformly across space? Okay. If these dots represent crimes, is this an area with high crime rate? Well, maybe not, right? Maybe it's just that the opportunity is there, right? That this is not a high crime rate area, but this is the banking row and there have been a lot of bank robberies, okay? Or, something else like that. Maybe it's where the bars and restaurants are and there's a lot of targets of opportunity for people who are looking for a quick mugging. Okay? Doesn't mean that the area itself is high crime rate. All right. Let's go ahead and give you a chance to answer another set of questions. So once again, I'm going to send you to the Google form. There are a bit more instructions here for especially this first one, which looks a little odd, but I want to just give you a vocal version of it too. So here we have an analysis where there is a simulation study being conducted. So these kinds of studies are like, okay, we have a model of how we think disease spreads. So we think that, people would catch illnesses from the water when there's more bacteria or whatever in it. Okay? We think from measurements, usually, that the longer the water has sat around before flowing through the pipes into your sink, that the more likely it is to have large amounts of bacteria. So we have a model that works like that. Okay, so let's ask some questions. When we divide up a fake map into grids or regions like counties or whatever, and we randomly assign them to have different water ages, our independent variable in this model, then we then draw, using a roll of the dice, a few sets of sample points to see how many illnesses we get in a period of time, right? So if we have a certain kind of map like this on the left, and we do that, right? So we draw a map that's relatively large in area and not uniform, and we draw random samples in the simulation study using this idea that, we should see this kind of data. Well, we do indeed see this kind of data, that there's this strong correlation between how long the water is sat around and the number of illnesses per whatever, okay, a rate per 100,000 people, say. Okay? But when we do the same simulation study, but with a very different drawing of the regions, one which is much smaller in area and regular and compact, we do the same simulation with the same thing that you would expect to see that, but we don't now. Okay, so what's going on here? What explains this problem? No longer is there a clear relationship between age of the water sitting around and the number of illnesses we expect. So go ahead, do these problems, and that is really all I had for you today. I hope you enjoyed it, and I look forward to chatting again with you next week. Also, remember actually that Monday we have a guest lecture, so please show up for the live Zoom on Monday. Okay, it's at 3 p.m. on our regular Zoom link. See you all there.